All right, hey guys. Before we talk about Unit 2, let's talk about what we've covered and learned in Lesson 1, Unit 1. So we've talked about our study of Unit 1 was about functions and characteristics of functions. What does a function look like? How do functions behave? How do you know when the graph of an equation represents a function? We've also talked specifically about linear functions, absolute value functions, quadratic functions, and then we talked about piecewise functions. And one of the things that we talked about in that unit were transformations of functions. So in Unit 2, our study is going to be about exponential functions and logarithmic functions. And when we study those and when we talk about those, we're going to be focusing on the same types of things that we focused on in Unit 1, the characteristics of exponential functions, the behavior, what are some characteristics that are specific to each of these functions. And so we're just building upon our toolbox. We're adding to our toolbox another set of functions that are very useful to know how they behave and some characteristics. So, exponential functions. We're going to be working with exponential functions that perhaps are in the form f of x equals a times b raised to the x minus h power plus k. And I hope that you recognize a couple of things or a few things in this equation. You'll notice that this general form for exponential functions has an a, has an h, and a k, and that shouldn't be new to us. We've seen that before in a variety of different functions as well as functions in general. So what makes this equation different and what makes this equation an exponential function is the actual variable x. You'll notice that you have a b, which is the base, and x is the variable, and if you notice that the variable is in the exponent, that's what makes this an exponential function. So we're going to start out with just a basic exponential function, f of x equals 2 to the x power. Again, this is an exponential function because the variable, you know that because the variable is within the exponent. And here the base is 2. So this is going to be one of those that I consider a mama and daddy graph. And we're going to use this to help us determine some basic characteristics of exponential functions. So we're going to start by using your calculator to graph this function. I want us to then sketch the graph on the axes that I've given you, and then I want us to identify and talk about some of these things here that we have listed. All right, so in order to graph a function or to graph anything, you need to go to y equals, which we'll do. I will type in, we'll need to put the equation in y1. So I'll press 2. I have to raise that 2, so I'll use my caret key, raise that to the x power, which I'm using x, t, theta, and n for my x. All right, so I've typed in and I've got my 2 to the x in y1, and to tell the calculator to graph this on a negative 10 to 10 and negative 10 to 10 window, I'll just press zoom, and I'll choose standard, which is 6, so zoom, press 6, and here comes the graph. So first of all, let's look at this graph and decide, does this graph represent a function? And the answer is yes, the graph does pass the vertical line test. We are only seeing a portion of the graph based on the window negative 10 to 10 and negative 10 to 10. But this graph, let's go ahead and sketch this graph. One point to look at is this point right here. This graph does go through the point 0, 1. So when you draw it or when you sketch it, it doesn't have to be perfect, but at least let's hit that y-intercept. So the graph will behave something like this. I wish I'd have made the graphs a little bigger, but sorry. So put arrows at the ends because the graph does continue It is what we call a continuous function. There's no breaks or gaps in the function, and it continues in all directions, or in both negative x direction and positive x direction. So, all right, so we just said, yes, it does represent a function. Now let's talk about the domain. Now that we've got the graph sketched, and we just talked about the domain, the smallest x would be negative infinity. The largest x would be positive infinity. And because this involves infinity, this would be, remember, parentheses, not brackets. Okay, so now let's talk about the range. If you look at this graph, the graph really kind of looks like it is sitting on the x-axis and maybe even perhaps drops below the x-axis. But here's what I want you to do. Press the trace button. When you press your trace, you'll see you get your cursor. Now, let's use your left arrow key and move that cursor back in the negative x direction. Your x's, as you notice here, are getting smaller. -4, -5, and so on. But at the same time, I want you to watch your y values. Your y values are getting smaller also. Graphically, it looks like your cursor is sitting or is on the x-axis, which would mean that y would equal 0. But look at that y value. This y value is not exactly 0. Is it close to 0? Yes. But here, if we just continue to move our cursor to the left, watching those y values, the y values are never going to reach 0. Now, in just a second, the y values are going to have so many decimal places that the calculator needs to use scientific notation. And let's see when we get that. But you can watch, even you're moving up, there we go. Your cursor is still moving to the left for x's. Your y values now are still getting much smaller. When that y has the e to the -4, that means to move the decimal point, 7.9, move that decimal point 4 places to the left, which means you're going to put 3 zeros, excuse me, in front of that. But if you were just to continue to hold your left arrow key down, that y value is never going to exactly equal exactly 0. The graph never touches the x-axis, but it gets very close to the x-axis. So what does that mean about our range? Well, our range starts at 0, but even though it doesn't include 0, we're going to start it with 0. But to indicate that 0 is not included, we will use parentheses around 0. And then the largest y value of this function, because this graph continues as x gets bigger, your y values get bigger, then the graph, or the range rather, the largest would be indicated by infinity. And just as a reminder, infinity is not a number. Infinity describes the behavior of, in this case, the y values. For the domain, the infinities are describing the behavior of the x's. So once again, the range goes from 0 to infinity, where 0 is not included. Now we use parentheses, and even though we use 0, it would be too difficult to name the point or the value that is the closest to 0. So that's why we have to use 0 with parentheses. Okay, so now let's go ahead and talk about the x-intercept. Well, we just talked about the range, so it makes sense to talk about the x-intercept. If this range goes from 0 to infinity and does not include 0, and if the range never crosses the x-axis, that means this graph does not have an x-intercept. This graph does have a y-intercept. and that y-intercept is 0, 1. And if I want to make sure of that, I can press trace, and for the y-intercept appearing to be at 0, 1, when I press trace, all I have to now do is type in 0 and enter, and I'll see the cursor goes to that point, and I see the y value is 1. So my y-intercept is 0, 1. Okay, and there's some other things that we could talk about that I didn't list here that we did talk about in Unit 1, like the intervals where the function is increasing, the function, or the intervals where the function is decreasing, which is nowhere. We could talk about, does this function have a local maximum or a local minimum? And the answer to that is no, because this function increases everywhere. The function never changes from increasing to decreasing, decreasing to increasing. So there is no local max, there is no local min. All right, so that's just some basic characteristics of an exponential function. So let's now move to, let's look at and investigate the effect that H has on the behavior of this mom and daddy graph. So there's two functions I want you to look at, and that's f of x equals 2 to the x minus 1, and f of x equals 2 to the x plus 4. Go ahead and I want you to stop the video for just a moment, and I want you to, on your calculator, graph those two, sketch the graphs, and I want you to determine if the graphs behave the way you thought they might behave. So go ahead and hit pause, and then once you get those graphs, you can resume the video. All right, so hopefully you've had time to take a moment to graph each of these functions, and hopefully you have a graph that for the 2 to the x minus 1, you should have a graph that looks something like this. And I know that with exponential functions, sometimes it's hard to recognize exactly how far to shift the graph, actually for both of these. But hopefully what you notice, the first thing I hope you notice is that both of these graphs have been shifted horizontally. So 2 to the x minus 1 has been shifted to the right, and 2 to the x plus 4 has been shifted to the left. If you think about it, that's how the graphs of all functions have behaved in terms of h. H has always affected the horizontal shift of the function, and it has always shifted the opposite of what you think. All right, so here's how I look at this. When you look, sometimes it's best to have a focal point or a focus point when you're shifting. Like with a parabola, the shift would be, it's easiest to look at the vertex. Well, here, look at the y-intercept. If you focus on the y-intercept, this y-intercept for 2 to the x minus 1 has shifted shifted forward or to the right 1 unit. So that's where that point is. Now, I don't want you to think that that's the only point that was shifted 1 unit to the right. Every single point on this graph was shifted to the right 1 value or 1 unit. Here, this y-intercept, if you use that as your focal point or focus point, then this point you can see has been moved left 4 units. So 1, 2, 3, 4, and the graph still behaves the same way. Okay, so H affects the graph in the same way that it has for all other functions that we've worked with. All right, so the next one I want us to look at is let's investigate K. We have f of x equals 2 to the x plus 1, and f of x equals 2 to the x minus 4. When you put these two functions in your calculator, when you put these two functions in your calculator, be careful about how you type them in. Make sure that your cursor is out of the exponent before you type in +1 and the -4. So take a moment, pause the video, and graph those and sketch the graph, and then when you get those done, resume the video. All right, so let's see, did you guys get the graph? Did your graphs look similar to these? So hopefully you recognize, let me scoot this up, that the K value, the +1 and the -4, gave you the vertical shift for the mom and daddy graph. This function, the mom and daddy graph was shifted up 1 unit, so the y-intercept is at 0,2, and here the graph of the mom and daddy graph was shifted down 4. So your y-intercept now for this one is 0, -3. All right, so H and K has affected the mom and daddy graph in the same way it has on all the other functions. So now what I want us to focus on is the B value. Now B is something that we haven't talked about, but it's because, excuse me, the base for the exponential function is the number or the value that is being raised to the power of x. So here we're going to look at f of x equals -2 to the x power, and f of x equals 1/2 to the x power. So I'm going to have you pause the video again. When you put these graphs into your calculator, I want you to make sure that you use parentheses because it's very important that you do. Take a moment and pause the video, graph them, sketch the graph, what you see, and then we'll come back together. All right, so hopefully you got the same thing that you see here. F of x equals -2 to the x. I don't have anything graphed. I don't know if when you graphed that, you didn't see a graph either. F of x equals 1/2 x, your graph should look like this. The graph of the mom and daddy 2 to the x function, the 1/2 reflects the mom and daddy graph of 2 to the x across the y-axis. So 1/2 raised to the x power is a decreasing function with a y-intercept of 0,1 as well. All right, so now let's go back and let's talk about -2 to the x power. So the question is, why are we not seeing a graph? Okay, well, let's go back to, I'm going to pull this down, and I want to go back and revisit the mom and daddy function of 2 to the x. So this is your basic exponential function, okay? We said the domain for x could be, are all real numbers, -infinity to +infinity. So I'm going to now go back and let's talk about what happens when that base is negative. So we said that x can be any number. All right, so let's play around with this a little bit. If I take -2 and I raise it to the, second power, I get 4. And what if I take -2 and raise it to the 1/2 power? Well, wait a minute. Well, x can be anything. X, we said the domain for an exponential function can be any real number. But let's talk about 1/2. 1/2 is a real number, so that's a legal value for x. But what does 1/2 actually represent? That represents, you could rewrite that as a square root. Well, if we rewrite this as the square root of -2, if you recall, the square root of -2 is not a real number. This is an imaginary number. So if the result of taking -2 and raising it to the 1/2 power is imaginary, then that must mean that 1/2 is not a value of the domain for this function. And if we have to exclude 1/2 as a value for this, then that means this is not an exponential function. So the base of an exponential function cannot be negative. So in other words, we must clarify that for an exponential function, b has to be positive. So we say b has to be greater than 0. When the base is negative, there are values for x that have to be excluded from the domain. But an exponential function's values for x is all real numbers. So the base can't be negative. All right, so the base we are saying has to be greater than 0. But now let's talk about, there's one value that's positive that the base can't be for the function to be exponential. And that would be a base of 1. What if the base of an exponential function is 1? Well, 1 raised to any power will remain 1. So that's a constant function, which would be a horizontal line. So we need to clarify again that the base of an exponential function will always be greater than 0, has to be greater than 0, except b also cannot equal 1. So the two real numbers, or not two real numbers, but the base of an exponential function has to be positive. It can't even be 0 because 0 raised to a power is 0. This also can't be 1 because then you have a constant function. So the question is, what does this graph really look like? I'm curious. Well, if we go back to the calculator, let me pull this in and let me turn this on. Let me go in and put -2, and when I do zoom 6, there's what it appears to be the graph, which is nothing. It looks like nothing has been graphed. But I want you to press trace. Notice that there's a cursor there and there's a point 0, 1. I mean, the calculator is giving us a coordinate for that point. I mean, you could do this for a variety of numbers. 2, enter. We could do -2, enter, and we get a value. But remember, what you have to remember is the values for x are the powers. Your base is still -2 for this function, but the power is x. Now type in a power of 1/2. So, and I'll use 0.5. So now 0.5, when x is 0.5, notice that we do not have a value for y, which means the function, this function is not defined for 1/2. So this is not an exponential function. We are not seeing that nice, exponential graph. So again, the graph of an exponential function the base has to be greater than 0. It also cannot be 1. All right. So now let's go in and let's finish out our exponential functions by looking at a. Now in for A has always been a coefficient. Let me pull this down a little bit. A has always been a coefficient, and it still is here. So if we look at f of x equals the mom and daddy graph or parent function 2 to the x, but if we have a negative on the outside, notice the difference between this equation and this equation. The difference is the negative here was inside parentheses, meaning the number, the base, is -2. Here, it's the opposite of 2 to the x power. So the a value is -1, and f of x equals a, which is -1, times the base 1/2 raised to the x power. So let's take a minute and let's graph these. Why don't you pause your the video at this point, graph those two, and then let's come back together and see what they look like. Okay, so now hopefully when you graphed each of these functions, you ended up with a graph that looks like this. Now, if you compare the opposite of 2 to the x with 2 to the x, and if you compare negative, or the opposite of 1/2 to the x power with the 1/2 x to the power of x, hopefully you notice that there's been a reflection, and the reflection is across the x-axis. And that's the way x, or the opposite of x, has always behaved. When the a value is negative, there's always been a reflection across the x-axis. So that is going to wrap up our exponential lesson. I'm going to end this video now, but what you should gain from this is that an exponential function, 2 to the x, increases everywhere, and the basic characteristics you can see there. So we'll come back and finish with part 2.